Welcome everybody. Today we are going to have a lecture on the introduction to quantum mechanics. Let me start the presentation. So now let's begin. The first part will be the Bohr model of atom. Then we'll discuss the classical model of hydrogen atom and the forces governing it. We'll move towards Bohr-Sommerfeld quantization schema, discuss psychical observables and operators, discuss energy conservation, superposition principle, act of measurement, and s- our presentations with acknowledgements and literature. First, Bohr model of atom. In this case, we'll be discussing the simplest case. One electron circling one proton. On this schema, we can see that the vector of velocity is orthogonal to the radius of circulation. Now we can discuss forces. Following equations ignore the loss of energy caused by the emission of the energy by the electron moving with constant acceleration. We have centripetal force and Coulomb force. Now, the centripetal force and the Coulomb force are equal to each other. From the equations for movement and electrostatic forces, we know there's two equations, which means that the mass times velocity squared divided by radius equals the charge squared divided by 4p epsilon 0 times r squared, which leads us to this simplified equation. Now, we also know that the velocity of the object circling another one is equal to 2 times p times radius divided by the period of circulation. And now, if we substitute velocity for this part of the equation, we can reach this. Mass times 4p squared times radius squared divided by period squared equals charge squared divided by 4p epsilon 0 radius. And now, if we simplify it to move radius and period onto left side, we reach this equation. Which correlates with the Kepler's third law about the constant of circulation around orbit. Now we will discuss the old Bohr-Sommerfeld quantization schema. Let's start with this. Now about moment equation that started it all. about momentum times radius equating the sum constant n and sum n multiplied by the Planck's constant with a bar. Now, this can be written this way, which, knowing that we have one atom, that we have one electron circling the center of atom, and the velocity equals 2p radius divided by the period of circulation, enables us to write it down this way. And now, if we move the period of circulation to one side, we know that the period of circulation equals 2p times r squared times mass times divided by some integer n times Planck's constant. Now we can move to this equation and substitute the period of circulation for the right side of this equation, which leads us to this. Now, all that's left is simplifying it, namely, simplifying this part, reaching the n squared times Planck constant squared divided by 4p squared times radius times mass squared, equating the charge squared divided by 16 times p cubed times epsilon 0 times mass, which leads us to 1 divided by r equals charge squared times mass divided by 4p epsilon 0 times 1 divided by n squared Planck constant square, which means that some particular R index n equals 4p epsilon 0 divided by charge squared times mass times Planck's constant times n squared times n squared. As we can see, all of these are constant. P is constant, epsilon 0 is constant, 4 is obviously constant, charge, in this case elemental charge, is constant, mass of particles are constant, and the Planck constant is obviously constant. So this means that only n really changes, which enables us to write it down as some 0th radius times n squared. The consequence of the quantization schema are discrete value system energies, meaning that all of the energies of system have some discrete energies. They are quantities. So, now let's move on to the basic assumptions of quantum mechanics. First, all physical observables are represented by operators acting on the quantum state. Energy. The energy operator equals imaginary value times del yes times change in time, rate of change in time. Momentum operator equals Planck constants divided by imaginary number, and here part about changing depending on position. The potential, the operator of potential function is essentially potential function. Operator of position is position. Not all observables can be measured at the same time. It is noticeable that the operator of momentum times operator of position doesn't equal operator of position times operator of moment. This implies that the operators of position and momentum are not commuting, so they cannot be both determined at the same time. If they are commuting, they can be both measured at the same time, which is also what uncertain, which is also why the Heisenberg principle of uncertainty is about. Now, principle of energy conservation, the second basic assumption. The energy of given particle equals its kinetic energy plus its potential energy, which is written like this. Now, if we substitute these values for their operators, we can reach this point. Now, if we use this operator equation on quantum state, in this case wave function, we can obtain the Schrödinger equation. In our case, the wave function is c from x position and t time. So now, the superposition principle. The state of the quantum system is represented by the Hilbert space vector. Superposition of various states is possible at the same instant of time and is expressed mathematically as the Hilbert vector from given C is the sum from n0 to infinity of some complex Cn times and vector. Now, this means that this wave function c equals sum of complex Cn times Cn from x and t. Also, we know that the sum of squared absolute values of Cn equals 1. The Cn in this case are related to the probability of given quantum state occurring. So the sum of them will equal 1. This now we also know that all Cn are orthonormal, meaning they are orthogonal and normalized at the same time. Now we will discuss the normalization condition as integral from minus infinity to infinity of some psi star k times psi n the delta x equating delta kn, which is the Kronecker delta. Now, the act of measurement in quantum mechanics. The fourth basic assumption is that the quantum system is evolving on n possible paths that coexist at the same instant of time, with some probability of occurrence. The act of observation of quantum system is interference of the external system, which causes the irreversible change of the observed system, collapsing its quantum state. Example. Before measurement, a qubit is a two-energy level system, where the psi from x and t equals c e1 times psi e1 plus c2 times psi 2, with probability of occurrence of given level equal to c e1 to absolute value of c1 squared for e1, or the absolute value of c e2 squared for e2. After measurement, we obtain the new wave function, psi after measurement xt. Of quantum object, we have the transformation of previous quantum state psi into psi-am. Now, the psi-am can have two outcomes. E to the power of e times phi e1 times psi e1 with probability of the absolute value of c e1 squared, or analogically the e to the power of e times phi e2 times psi e2 with probability of the absolute value of c e2 squared. Acknowledgements. I would like to thank to the Dr. Krzysztof Pomorski from the Krakow University of Technology and the firm Quantum Hardware Systems for his conceptual framework and guidelines used in preparation of this presentation. Now the literature. PAM Dirac, Principles of Quantum Mechanics, Richard Fitzpatrick, Quantum Mechanics, World Scientific Publishing, and James Binney and David Skinner, The Physics of Quantum Mechanics, Oxford University Press. Thank you for your attention. I hope I helped you understand the basics of quantum mechanics.